All right, we're going to begin section 15.1 in this video, which is vector fields. Or force fields, either one. So let D be a set in space, or just in 3 dimensions. A vector field is a function so we're going to use capital F, and we're going to put a vector hat over that, so they'll be bold facing your textbook in this section. That assigns to each point x, y, z in D a 3-dimensional vector the vector field F of x, y, z equals, so we've seen vector functions before. We were just looking at them in the previous chapter when we were doing parameterization of surfaces. So this itself is a vector function as well. So we've seen the functions with the vector hat. You put in a point and it gives you a vector. So here our output will be some function m of x, y, z will be our I component, and some other function n of x, y, z be our j component, and some function p of x, y, z be our k component. And for shorthand, as we go through this chapter, you'll see me write just m, n, and p as well as in the textbook group. So it's just understood that if you see f of x, y, z, then m, n, and p are functions of x, y, and z. If you see f of x, y, then m, n, and p are functions of x and y. All right, so let's look at an example. We're going to sketch f of x, y equals 1/2, comma, y minus x. All right, so we're going to sketch this. So this is, I gave the definition of vector field in terms of a function of 3 variables. We can also talk about it for a function of 2 variables. So we're working in 2 dimensions now. So we sketch our coordinate axes. So now what we do is, now we rarely ever sketch these by hand. I'm just going to do this just so you get an idea of how a vector field works, and you'll also see why we don't sketch them by hand. You just pick, because this can take on any points x and y. So you pick points x and y, you plug them in here. It's going to give you a vector. You plot the vector at whatever point that you plugged in. So for instance, we'll start with 0, 0 to make our lives easy. So we're going to start at 0, 0 right here at the origin. When we put 0, 0 in here, we get 1/2, comma 0. So we're going to sketch the vector 1/2, comma 0 starting at the origin. So we go over 1/2 unit in the x direction and go up 0 units in the y direction. So we would just get that vector right there. Put 1 right there. So at 0, 0, we get that vector. Let's put in whatever. Let's do -1, 1. So we do -1, 1. So we're right here. We're going to start our vector right here at -1, 1. So I'm just going to put a point right there because I know that's where I'm going to start my vector, but I don't know which way I'm going to go. So when I put in -1, 1, that's always 1/2. -1 minus -1 just gives me 0. So I get 1/2, 0. So I get that same vector I got right there, but now we start at -1, and sketch it. And let's do a couple more. Let's do, let's say for instance, if we were to do, I don't know, 5, 2. So if we do 5, 2, so well, let's do 3, 2 since we can stay on our axis. So 3, 2. We'll say 3, 2 is about right. We'll say the point will be right there. That's going to be our starting point, 3, 2. So now if we put 3, 2 in there, that's always going to be 1/2. And then we put 3, 2 right in here, then we're going to get 2 minus 3, which is going to give us -1. So now we're going to go, starting right here, we would go in the x direction 1/2, and then we would go in the y direction -1. So we would end up with a vector that looked like that. And we'll do one more. Let's do one over here. Let's do -1, 1. So we do -1, 1. We're about right there is where we're going to start our vector. We're going to plug in -1, 1 to here. So 1/2, that's always going to stay the same. For this particular vector function, vector field we're talking about. And what did I say we're doing? -1 and 1. So we're going to get 1 minus the -1, which is going to give us 2. So we're going to go over 1/2 and then up 2. So we'll get something that looks like that. So notice this is why we don't do this by hand. We normally use a computer algebra system if we want to plot a vector field. Now, what are these used for? So this would be used if we want to get an idea of, say, and remember I said a vector field or a force field. So we can look at this as a force field where these are forces. So if a particle were to start in any particular point, if we had a lot more arrows drawn in here, we could get an idea of how the forces would act upon that particle and how it would travel in the force field. So we're just going to pretend if I had more arrows here. So maybe if I had a lot more arrows here, I might find out if a particle were to start right here, it would follow those 2 arrows and maybe come up here and then go back in this direction or something like that. I would need a lot more arrows to actually tell what happened in this area or what happened down here for that matter. But this is what we would use a vector field or a force field for. So this is not the first vector field that we've seen or that we've discussed. So one that's familiar to us is, so a vector field with which we are familiar is the gradient of f at x, y, z, which is the vector whose first component is the partial of f with respect to x, second is the partial with respect to y, and third is the partial with respect to z. We call this the gradient vector field. All right, so next thing we want to talk about is what's called a potential function, and we'll use these a little bit later, but I just want to go ahead and get the definition out the way now. So given a vector field, a vector field F is conservative if there's a scalar function F such that the vector field F is equal to the gradient of that scalar function. By scalar function, I just mean the type of functions we would work with before we were in this class, or the type of function we would work with in a Calculus 1 or Calculus 2 class, or the type of function that we work with in here, like in our integrand. So some function f of x, y, z that gives you a real number. So that's what we mean by a scalar function versus a vector function. You put in an x, y, z and it gives you a vector. Scalar function, you put in an x, y, z and it gives you a real number. All right, such that f is equal to the gradient f. In this case, f is called a potential function. So two things we're defining here, what it means to be conservative. So if I give you a vector field and you're able to find some scalar function f such that the gradient of f is that vector field you were given, then that vector field is said to be conservative, and that scalar function f is called a potential function. Please try to keep in mind that this is our definition of conservative, is this, because later on we're going to have a characterization of conservative that it just gives us a criterion under which a vector field is conservative, but that's not to be confused with the definition of conservative. This is what it means to be conservative. All right, so now let's talk about curl and divergence. So let's go to the next page. Given a vector field f of x, y, z, which equals the vector whose first component is m of x, y, z, second component is n of x, y, z, and third component is p of x, y, z. The divergence of the vector field f, denoted divergence of f, is given by the divergence of f is equal to the partial of m with respect to x plus the partial of n with respect to y plus the partial of p with respect to z. And notice the divergence, when you take the divergence, this thing is, you would put in a point, we will be putting in a point x, y, z, and this that you get here is just going to be some scalar value. And then the next thing we'll define is the curl, and then we'll go back to talking about conservative vector fields or potential functions. So given a vector field f, all right, so now just for shorthand notation, I'm going to drop the x, y, z on here, 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 and here. So f equals, and actually we'll write it in terms of I, j, and k, just so we're accustomed to seeing both. f equals m times I plus n times j plus p times k. So same thing as we had up there, just different notation. The curl of f denoted curl of f is given by curl of f equals I, and then this is just a notational thing, and I'll explain how to do this. The partial with respect to x, but not the partial of anything, so we just put the partial notation there. And then m and j, partial with respect to y, n, and k, partial with respect to z and p. So it's kind of like we're doing a cross product between this thing and that down there. So when we go through and we do this, we get this as equal to p sub y, and I'm going to now use the shorthand notation for the partial. So because we know how to do cross products, you would ignore this first column and the first row, and you would take the partial of p with respect to y minus the partial of n with respect to z. So minus n sub z in the I direction. And then remember, for the j component, you have a negative sign. And then ignore that column. And then a partial of p with respect to x minus the partial of m with respect to z. The j direction, and then plus the partial of n with respect to x minus the partial of m with respect to y in the k direction. All right, so I'm going to stop this video here, and then in our next video, we'll do some examples of curl and divergence, as well as look at finding a potential function.